For our MAE 152 final project, we analyzed a quadcopter drone. For the propeller, we evaluated three designs: an initial three-blade propeller with filleted joints, redesign number 1 with a larger center diameter but no fillets, and redesign number 2 which added fillets to the larger center. The additions were intended to reduce the stress experienced at the bases of the blades. We analyzed 4 different scenarios, the first 2 modeling hover and a cantilever test. The second redesign successfully reduced experienced stresses at the base, but the first redesign saw a stress concentration at the base of the blade due to the sharp corner. The last 2 modeled a collision during flight and a modal analysis to determine its natural frequencies. The redesigns did not save the propeller blade from breaking in an impact, but it did show some increased performance. Here is the SN curve for the specific strong carbon fiber used in the propeller. During hover, the initial design has a very healthy fatigue life, surviving over 200,000 flight hours before failure. We evaluated 3 propeller guard designs: the initial 3-spoke layout, redesign number 1 with a top circular support, and redesign number 2 with a bottom support. These additions were intended to increase overall assembly stiffness. Testing across side, impact, drag, and modal frequency showed that redesign number 1 was best for impact, while redesign number 2 reduced drag stress by over 10%. Both iterations slightly lowered the natural frequency, confirming that added mass shifted the harmonic response. Comparing 1D theory to FEA showed a 96.7% deflection error. This highlights that simple cantilever equations ignore the root fillets and load sharing of the outer ring. The analytical model is a conservative worst case, while FEA captures a true 3D rigidity. For the landing gear, we evaluated 3 designs: the initial design, a first redesign where fillets were added at high stress regions, and a second redesign where the struts were thickened to improve structural strength. We analyzed 2 main loading scenarios: a normal landing case representing the drone's weight and a hard landing case to simulate impact conditions. From the results, both redesigns reduced stress compared to the initial design, but redesign number 2 showed the best performance, lowering maximum strength to about 0.539 megapascals during impact while also reducing displacement. We also ran a modal analysis where redesign number 2 increased the natural frequency significantly, indicating a stiffer structure and better resistance to vibration. We evaluated 3 drone body designs: the initial carbon fiber frame, redesign number 1 focused on weight reduction by removing material from the upper and lower plates and arms, and redesign number 2 which introduced a truss support structure. These changes were intended to reduce weight while improving overall stiffness and load distribution. Testing across battery loading, drop impact, and modal analysis showed that both redesigns significantly improved the performance over the initial design. Redesign number 1 reduced stress and displacement through weight reduction, while redesign number 2 performed the best overall, reducing stress by nearly 69% and displacement by up to 36%. It also increased the natural frequency to 167 Hz, indicating a stiffer and more stable structure. For the drone arm, we evaluated 3 designs. The initial design had sharp corners, so redesign number 1 addressed this by adding filleting to the sharp corners and edges. Redesign number 2 added on by increasing the thickness of the arm entirely. These were intended to decrease the stress the component experienced. For our analysis results, redesign number 2 proved to be the most optimal design, as it significantly reduced the maximum stress by about 28% and similarly decreased the maximum displacement by about 29%. That's all, and thank you for listening.